Hello, this is Videsh Ray, and today is going to be a video on like the topic of like basic complete search. So it's another like USCO topic, USCO bronze topic. And yeah, so basic complete search problems are basically problems where you can look through like all the cases of a solution and like find your answer through that. That's why it's called a complete search. You're just looking through everything. And it's mostly just a brute force type problem. So they're usually pretty simple. And yeah. So I've looked at two problems to be example problems. So the first one is called maximum distance. It's a code forces problem. And yeah. So I have my file here, my coding file. So we can just go ahead and start. And you can also like pause the video and read the problem statement or something to think about it. But it's pretty easy, so yeah. Okay, so just like setup. Uh, okay, so first we're gonna take n as input, right? And n is just the number of x and y coordinates they'll give us. So here's the problem statement, right? So there's n integer points on a coordinate plane, and we have to find the square of the maximum Euclidean distance, aka the length of the straight line between any two of the points. Okay, so yeah, and this is like the input format. They give us n, then they give us n x values, n y values. So yeah, okay. So let's make a vector of size n for the x's and a vector of size n for the y's. And then we can go ahead and take our input. Oh, yeah. Yeah, so now we've taken our input and now we have to find our answer. So what we can do is, again, this is a complete search, it's just a brute force. So first let's initialize our like answer to 0. That's like because we don't know yet, so we'll just like assume like for now we'll just set it to 0, like that's a base value. And then yeah. So now remember we have to look through all the pairs of x and y, like the all the pairs of points and check all their distances. So first let's pick our first um point, so P1, point 1. And P1 will start at like the first point, so 0 indexed, of course, so that's why it's 0 to less than n. Um, and now once we have our first point, then we also have to go and look at the other points. So this is our second point. So we can set P2 equal to P1 plus 1, and then yeah, P2 less than n, P2 plus plus. The reason we'll do P1 plus 1 and not just like 0 to n is because P1 is like when we do P1 and like P2, um so for the first loop we would be going from 0, like for the first loop here, for the first outer loop, the first time it runs, we would be looking at the first point and comparing it to all the other points that come after it. So then if we look at a point that comes after it, let's say some point that comes after it and that eventually becomes our P1, then we should only compare it to points that come after it, because if we compare it to points that come before it, like we've already done that. So that's why we initialize P2 to P1 plus 1. Okay. Now once we have that, um yeah, now we have that set up. So now we just have to look at distance, the actual distance now. Um yeah. So answer equals max between answer and the current distance. right? So the current distance would just be um absolute value of x of p1 minus x of p2. So first of all, this will give us the distance between the two x values and uh, the absolute value of that, and then we're going to square that basically. So times absolute value of x of p1 minus x of p2. So I mean, okay, why we're doing this is because a squared plus b squared equals c squared, right? Essentially, right? So in this scenario, in this problem, uh, a is going to be the distance between the two x's, like the x's of the 2 points, and b is going to be the distance between the um y's of the 2 points. And then c will be like the c squared will be the squared Euclidean distance. Um, and yeah, c will where c will be like the actual distance, and c squared will be the squared Euclidean distance. Now we don't need c because they ask for the square of the maximum Euclidean distance. Okay, so yeah, so we each have to do that plus, so we have the a squared part done, now we need the plus b squared. So plus absolute value of y of b1 minus y of b2 times absolute value y of b1 minus y of b2. Yeah, and then at the very end we just output answer. So yeah, like I said, like pretty straightforward and pretty simple. And yeah, we can just copy the input real quick. Yeah, so our input matches, I mean our output matches 1059112. So yeah, and we can upload it. Let's see um how well it goes. And that's while that's happening. Um, 1 second. Now let's try to simulate it. Okay, there we go. We finally got it running. Okay, while that happens, this is the next problem, called diamond collector. So you just like you can pause and read the problem statement, think about it. Yeah. So the problem statement is basically that Bessie the cow has always been a fan of shiny objects, and now she's taken up a hobby of mining diamonds in her spare time. So she has n diamonds, where n is up to 1,000 of different sizes, and she wants to arrange them in a display case. And Bessie wants the diamonds to be relatively similar in size, so she decides that she won't include any two diamonds in a case, in the display case, if their sizes um, differ by more than k. So if their sizes differ by exactly k, then they can be displayed together. Yeah, and then given k, help Bessie determine the max number of diamonds she can display in the case. Also, if we look back at this, our solution submitted for that. So yeah, we're good with that. And yeah, let's move on to this problem now. So like you can pause and think about how you could solve this. And yeah, so I'll explain it now. So the solution is basically to you literally just want to pick a certain diamond and then look at all the other diamonds and see which ones are compatible, and like you're gonna get a value for each diamond, like the number of ones that are compatible for it. Um, and yeah, you just want to compare those values and see which one gives you the highest result. And yeah, that's pretty much it. So yeah, and also this is an easy rated problem on USCO Guide. Okay, so okay, I just coded that on the other file. It should be on here. And yeah, now we can just go ahead code for this problem. So first we'll take the input of n and k. So the number of diamonds and the max size that they can differ by. And then we'll make a vector for the diamonds. We're gonna take input. Okay. Now what we're gonna do is first let's pick a certain diamond. So we're gonna start with diamond like from 0, right? Um yeah, so now after we look at that diamond, now we want to look at other diamonds, right? So for LLJ, so like these are the diamonds we're gonna compare with. LJ equals um 0, J less than n, J plus plus. And we're gonna have like I'll have a variable called current for like the number of diamonds that are compatible with this diamond. And also we'll have our answer variable. Yeah. So now what we'll do is uh if the absolute value of diamonds of I minus diamonds of J is less than or equal to K, right? Because that was what was the condition, right? The um the difference between the diamonds like had to be like at most K. Okay, after this we need one more condition. Because if we only have this one condition of the absolute value of diamonds of I minus diamonds J less than or equal to K, well, what could happen is that when we're comparing like any jth diamond with the ith diamond, um we since it's absolute value and we're comparing by that, we could come across two like diamonds, say like one of the diamonds is K less than the ith diamond, like the size, and another diamond is K more than the ith diamond size. So then what would happen is then those two diamonds could potentially like differ by like 2K, right? So like if you have a diamond below and above, like um that could mean that you're gonna have a new smaller like you would have a new smallest diamond. So then you're not, if you just compare it to diamonds of I, then you're not accurately looking at checking if like the new diamond is within the bounds or not. So what you want to do is whenever you're looking at the diamonds, first check if the two values are within like K of each other. And then you also want to check and make sure that diamonds of J is greater than or equal to diamonds of I. And if this is true, then you do current plus plus, because like now you see that this diamond is compatible, so just add 1 to your current value, like the number of diamonds that are compatible, right? Current equals the number of diamonds that are compatible, that are currently compatible. Okay, and basically why all you have to add is diamonds of J is greater than or equal to diamonds of I is because so if you check that the jth diamond is greater or equal to the ith diamond, that means that the the smaller bound of the diamonds, right? So if you have some diamonds in display case and you start with diamond like the ith diamond, right? You start with diamond I. If you're making sure that every new diamond that you're looking at and considering, if you're making sure that every diamond is greater than or equal to this one, that means that you won't have like a smaller one come by. You won't like accept a smaller one. So that means that you'll never run into the issue of one diamond being smaller than the ith diamond, the other diamond is larger than the ith diamond, and somehow like those kind of like collide and like you get a distance greater than k in your case, like between two diamonds. Um, and this will take care of everything because here you're starting from I equals 0, I less than n, j equals 0, j less than n. You're going through like everything. So basically what's happening is that at a certain for like this iteration in the loop, you're setting the size. So you're setting diamond diamonds of I is equal to the smallest diamond for this iteration. Okay? So for each iteration, you're setting diamonds of I to this as the smallest size. So diamond I will be the smallest diamond for the iteration. And that's how it works. Now, you could do this differently if you wanted to sort it, but under this like problem type, like you don't even need to sort. You can just do this like brute force complete sort. Okay, anyways, now what you'll do is after that inner for loop, um, after that inner for loop, you'll have the current value. So you'll have all the diamonds that are currently compatible. So then just do answer equals max, answer, and current. And then at the very end, once you're out of all the loops, you just want to print your answer. Um, and yeah, and also this is file input output. So you want to open those files. So diamond.in read stdin uh, f4 reopen diamond.out std out. And I already made my in and out files, so we can just run it. So this is the sample input. I already put it in here. Um, yeah. So here we can just run it real quick and see what happens. And the output is 4, which is correct. Yeah. And also when you're in your inner for loop, like um, you don't want to. So you might think that you have to do like if I is equal to j, then like skip this loop or something like that. But you don't want to do that because um you're saying that the diamonds of I is the smallest diamond for the iteration, but you haven't actually considered the like putting in the I diamond yet. Like you know it's going to be the smallest one and you set it as that, but you haven't actually put it in like your number of diamonds that are compatible because obviously the diamond is compatible with itself and you haven't like included that yet because you've done current is equal to 0. So when you're in that inner loop, all of the diamonds are getting checked to see if they're compatible. So even the like the diamond, the ith diamond itself will get checked in this inner loop. So yeah. Okay, now we can try and submit that. And like I've solved this before, so that's why it's showing up like that. Yeah, so diamond collector.cpp, yeah. Okay, yeah. So we got a full AC. Okay, and yeah, so that was just like the topic of basic complete search and some two example problems. Yeah. So thank you. That was it for today.